All right, guys. So what we're going to be doing for this video is we're going to be taking a look at how we can package sort of some standard designs into symbols so that we can use them in more complex schematics and designs without actually having to manually place every single transistor, since that can get out of hand pretty quickly. So we're going to assume at this point that you've kind of gotten the feel for the schematic layout. So you can see here I've got an inverter schematic up and running. It's not a very good design because of some of the parameters aren't set correctly, but that's just what we're going to do. So I'm not giving you the 100% right answers for class. So we're going to stick with this design. If you are a little bit confused on how to get to this point, go back and watch the previous video since we cover pretty much all the information you need to get to this point. So how to place down transistors, these ground and VDD symbols, also the in and out pins. So if we are going to start from this point, what we're going to start thinking about is if we're going to have more complex logic designs, we don't want to have to manually place every single transistor since, like we said, that can get out of hand pretty quickly. And if you have millions of transistors, that's going to be a lot of work for you, especially whenever you're troubleshooting and trying to figure out where things are going wrong. So usually it's very handy if we can use symbols. So if we can sort of abstract these things like this design into just an inverter symbol, and then we can have something going on our input, and we have a pretty good idea of what we're going to get on our output. And then instead of having to use two transistors, these two symbols here, and then these wires, we can instead just use a single inverter symbol with an in and out wire. So to get started making a symbol, what we're going to do is I'll go ahead and maximize this screen, press F to bring it all into full screen. And what we're going to do is we're going to start off by doing this create, and then we're going to go down here cell view. So the symbol is a whole nother cell view. So we're going to start off by create cell view. We're going to create a cell view from a cell view. We're going to use this schematic and the pins that we have declared here in order to make a new cell view. So we just need to make sure that we have it set to symbol, and this is schematic symbol. This should be pretty default. Okay, and then it's going to bring up this page here. Now you can see that for this inverter, we only have two pins in and out. If you want it to be maybe a little bit more complete, you could also add a VDD and ground pin, but for us, we don't necessarily care about that right now, although maybe in the future it'd be good practice to have a specific VDD and ground pin if you need that. So what we're going to do here is we're going to decide, Cadence can't really do everything for us, so it's not going to make us an inverter symbol with a triangle and a dot at the end of it, but it will make us just a generic box symbol. So we just need to tell it what side all those pins go on. So if it's box, it's got four sides, left, right, top, and bottom. And we're going to tell it just where to start those pins off. So for an inverter, we're just going to assume that the left is going to be our input. So we're going to put in there. And then our output is going to come out of the right side. So we're going to put out on the right. And then for the top, if we wanted top pins, we could put something here. Like if we were going to do VDD on the top and ground on the bottom, we could do something like that. For us, we don't really care about that. So we're just going to leave it as left pin is in, right pin is out, and then we're going to leave everything else the same, and then just press OK. Now, once we press OK, it'll open this new window. It's going to ask if it's OK to overwrite. So since I've been working in this library a little bit before, I might get this. So I'm just going to press yes. So whenever we create a new symbol, we're usually going to want to rewrite the old CDF file. So I'm just going to hit yes. Now we can see that it has opened us up a new screen, press F, and this is going to be pretty much what our symbol looks like. So if we were to make a new schematic and we wanted to create an inverter instance, this is what the symbol would look like. So the symbol for a PMOS is this guy, symbol for an NMOS is this guy, and if we now place an inverter, then it would look something like this. But this isn't very descriptive, right? It's not really telling us what the inverter is. We can't just glance at it and tell that it's an inverter, although it does have a part name and an instance name here that would hopefully say inverter. We can't really guess it just at the beginning. So what we're going to do is we're going to modify this symbol just a little bit. So you can see here we have this left pin here, our right pin, which is our out. We don't want to mess with these quite yet. But what I do want to do is I want to start maybe moving some of this text around a little bit. What I'll do is I'll click this red instance name, click M to move, and click one more time to move it, and I'm just going to move it over here. I'm going to do the same thing. Click this guy, press M, click one more time, and I'll move him to the bottom. So you don't have to do it exactly this way. This is just sort of getting it out of the way so that I can work with this cell view a little bit more. So I can work with this view. Now, I don't really just want a box. I want to have that sort of triangle and a dot or a circle at the end. So let's just get rid of this box. So if I select part of this box, like if I select here and then press delete, I can click it one more time, and then it's just going to delete our entire box. So now we don't have a box. Our symbol's not looking too good right now. But what we can do is that we can now just create a triangle. So to create a triangle, we have to first go to the Create menu here at the top. We're going to go to Shape. It doesn't have just a built-in triangle option, but we can get a triangle by doing just a polygon. So we're going to do a polygon. Make sure we have polygon selected. Fill style, we don't want it to be filled. We just want it to have an outline. And for our draw mode, you can see here we have these straight lines here, 90-degree angles, these 90-degree angles, 45-degree angles, and things like that. We're just going to stick with this straight lines. We're not necessarily working on 45 degrees. Okay? I'm going to hide this, and then I'm going to start drawing the vertexes of the polygon. So I'm going to start off in this top portion right here. I'm going to click. That's going to tell it to start drawing. I'm going to drag it down, and you can see that it's starting to draw a line. Now, if I click here, then it will set this point. So now if I move around, this line right here is set. Now I can continue on this way to make an inverter symbol. So if I try and keep everything centered, I can keep it aligned with this pin here. I can move it maybe over here, click one more time, and then move back to the beginning, click one last time. Once we make it back to the beginning, then it will actually stop with the drawing and it'll say that we have this finished. So we have this polygon finished. Now for a polygon, we can't create a circle with a polygon. So instead what we're going to do is we're going to do create. We're going to do shape, circle. You could do an ellipse if you want to, but I'm going to do a circle. And then we're going to keep it the same way. We want it to be an outline and a circle. Press hide here. Now we could try and start it from this center point here, but what you'll see is that that's actually just setting the center point itself. That's not going to kind of give us a lot of control over it. What I like to do is I like to just pretty much hit escape, do create, shape, circle. And I like to make just a small circle anywhere. So about the smallest I can make is yay big or so. Could make it a lot bigger, but if I did make a circle like right here, then I'm done making the circle. I can press escape. Now I can just hit M to move it, click it, and then bring it over so that it's touching. That makes it work a little bit easier for me, but you can do however way you want. So if you want to start off here, maybe you can start off clicking your center of your circle right there and then stretch it so that it's touching the edge. Now we don't have this portion of the pin, or we don't have this output pin connected, and we don't want it to just be out here floating. What we can do is we can actually click and hold and then drag. So if we can maybe come out here so we're not selecting this area, click, drag, select out and the pin. Then once we have them all selected, we can press M, move it over. Now what you'll see here is that now we have the pin kind of connected where it should be, but this out doesn't look like it's connected in the right place. So what we can do is we can actually just select it. So if I select it, press M, and then click it one more time, I can actually move it over slightly so that maybe it's sitting just right here. So if we were going to have it match, I'll do the same thing with in. And now it looks like we have a pretty good symbol. Now, one thing that you also notice is that this bounding box right here kind of extends beyond what we need it to. So before, whenever we had a large symbol, we needed it to go all the way out this far to the right. But for now, we don't need it to go that far. So we can actually just click and either hit S to stretch this one edge. Or if I undo, what you can do is I can hit Control D to deselect everything. Then I can just click this edge, drag it over. So either one of those works for moving the sort of bounding box over. And once we get to this point, we can press F, move this instance name and part name around a little bit by pressing M and then selecting it. So we can move it around so that they're a little bit more centered. And now that looks like we have a pretty good inverter symbol. So what we'll do is we'll just hit save and check. What it'll do is it'll make sure that you have the correct number of pins. So since we only have 2 pins on our schematic, we only need on our symbol. So if we had, let's say, for example, if I delete this pin here, I try to save and check, then we'll see that we get a warning here. We don't have all the pins. So hopefully I can undo and bring that back. So here what I'll do is I'll just create pin. We had it set to input output previously. For our type, where hopefully that'll be what we need it to. And we'll just name it in. Let's make sure this is look. Okay. So now we've gotten ourselves another pin, and I can just move this back where it was before. Hopefully we can save and check. See, we got a little visual glitch there, but save and check, everything works out. So now, if we save and check one more time, I'm just going to go ahead and close this. And what we can do is we can actually open up our library manager, and now we can see that this inverter has a symbol. So we have our inverter symbol here, and it has an associated schematic. So pretty much any time that we use this symbol, that symbol that we just made, inside of that symbol is going to be this schematic here with the input and output connected. So this lets us sort of abstract some more complex designs. So if we're going to do something like, let's say we're going to try and experiment a little bit with some simulations, what we can instead do is, instead of having to place voltage sources here and connecting our VDD and ground, we can actually just use our symbol now. We can use our symbol, and I will go ahead and just close this guy. We'll open up the library manager, and I'm going to use the same library that I've been working on that has my inverter cell in it, but I'm going to make a new cell. So I'm going to go ahead and say File, New. I'm going to make a new cell view. Now, what I need to do here is, since I'm making a new cell, I'm not adding a new view to inverter like a layout or anything like that. I'm actually going to make a new cell where I'm using the inverter to do a simulation. So what I can do is I can make one called maybe INV_TB for test bench. And we want it to be a schematic. So we're not going to do any sort of layout and thing like that. We want to start off with a schematic. So if we press OK, now we can see in our library manager, we have this new cell with a schematic in it called inverter test bench. I'll maximize this guy. Now, what we need to place is we need to place our inputs. We need to make sure we tell it what our output is going to be. And then we also, excuse me, we also need to give it VDD and ground. So the first thing I'll place is just the inverter, because that's the device that we're going to be trying to test. So to place the inverter, we're going to use I to bring up the instance window. And now for the library, instead of using NCSU analog parts and selecting like NMOS4 or something like that, we actually want to use a design that we made. Right? So we're going to use a design that we made. So instead of using an NMOS4, we're going to select the library that we just used. So mine is called AC_symbol test. For the cell, we are going to pick the, not inverter test bench, but the inverter. So I named mine inverter. Whatever you name yours, if it's OR, INV, whatever it is, you just need to pick out whatever that cell is that you just put a symbol for. And now you can see that we do have a symbol. If we place it in our schematic, we now have what looks like an inverter. We have this I0 here. It's got its name, inverter. So even if we weren't doing a good job on making our symbol, we can still tell that it's an inverter, and we in and an out. Now, one thing you can do is if you just want to double check what's actually underneath here and what this symbol represents, you can actually click on this guy and right click, and you can see that there's descend edit and descend read. So if we just want to view what's underneath it, we can click X or go to descend read. It'll pull up this tab. It's the descend tab. And we're going to look at the schematic view for read, and we're going to open it in the current tab. What we'll see is if we press OK, now this window changes so that we have the same schematic from before. And I can't change anything because we're in read mode, so it'll get mad at me if I try and delete something. But we can go to View, Edit, and Hierarchy. We can see that we can press B to return or Shift B to return to the top. Either one will do this. Now, if I actually wanted to edit, I could click on here and press Shift X. And you'll see that now we can descend for an edit. Press OK. And now if I wanted to do something like delete that delete that transistor, then I could. Press U and undo it. Or I could maybe change some of these variables and things. I need to make sure that I save and check, otherwise it'll get mad. You can also use these symbols here. So this up arrow will take you up one level, and this one will top. So now that we kind of get a sense for what's inside this inverter, now we can start adding some of the other sources that we need. So let's go ahead and add an output. So our output, we could just have a wire going straight out, or we could add something that tells us it's connected. But for us, we want to make sure that it's going to work whenever we are driving a capacitive load. So if we're going to try and simulate the output that's having some sort of capacitance, maybe it's the input of another gate or the output to the physical world, either way, we're going to have some capacitance. To add a capacitor, we can just press I. We're not going to go to our own library. We're going to go to the analog library. For the cell, you just press C. You can see the first thing that comes up is cap. So we press tab, select cap. That's our capacitor. And then we can set the capacitance here. So if I set it to maybe something, let's make it like maybe 500 femtofarad, just some random number. Then I can add this capacitor to the output here. I can press I again, that instance window. Now I can add maybe a few ground symbols to show that this other side is connected to ground. W, wire the output to the input of the capacitor. Now we have our output wire. And we can do the same thing on the input. So if I press I, we can add a VDC. So we could add a DC voltage source if we wanted to. So if we wanted to maybe see how the input versus output looks as we sweep DC, we could do that. Or if we're going to do a transient simulation, which you may need to see rise and fall times or see how well balanced or how good of a design you have, then what we can use is we can use something like V-pulse. So V-pulse, it's going to be a pretty much square wave. So you can see that if we look at the schematic symbol, go ahead and place it down, we have a voltage source and then this little square wave symbol here. That's going to tell us pretty much that this is going to be a square wave voltage source. Now I'll go ahead and connect this guy. I'll press C to bring up the copy tool, copy the ground and bring it right here. Now if we select this guy and press Q, then we can actually look at the properties. The properties are going to tell us quite a bit about the way that this guy works. So we can see we've got a couple of these parameters up here at the top that we don't really mess with. We've got a DC voltage if we're going to do a DC simulation. Then we also have AC magnitude and phase if we're going to do an AC simulation. But what we really care about all the way down here. So once we get down below voltage 1 and voltage 2, this is going to tell us whether we are, or the voltage 1 is kind of like the off voltage, voltage 2 is kind of like the on voltage for this square wave. So it's going to alternate between those two. Now, if you've done simulation before, you know that it can be good to make everything parametric. So you don't want to hard code everything. So for example, I hard coded this capacitor size, and maybe the transistor sizes are currently hard coded, but we can fix that here in a moment. But for now, what I'm going to do is I'm going to try and use parameters whenever I'm defining these different voltages. The voltage 1, let's say for an inverter, our voltage 1, our off voltage is going to be 0 volts. That's kind of just a given, so we don't have to worry about changing this guy. But for this one here, we could have a VDD of 5 volts, could have a VDD of 3.3 volts. So for now, let's go ahead and set this to just something, a variable called chip VDD. Okay. You can see that it added a V at the end of it, so that tells us that we're good and it's recognizing it. Now, our period, we're going to do something similar. So usually the symbol for period, it could be something like T. So that's going to be the time it takes to complete one period. For the delay time, that's going to be the amount of time initially before this guy turns on. So that's going to be pretty much the amount of time it starts off at 0 before it goes to VDD. So if we want this to be kind of balanced, I'm just going to make this T over 2. So T divided by 2 seconds. So if the period is 10 nanoseconds, then the delay time will be 5 nanoseconds. 5 nanoseconds off, 5 nanoseconds on. Rise time, I'm going to do TR here for the T rise. And then fall time, I'll also keep it as TR so that it's symmetric. Pulse width is going to be pretty similar. So if we start off at 0, then we're going to go to our 1 or our high voltage. We want to tell it how long that pulse is going to be. So if we want it to be symmetric, we'll do T over 2. And for our temperature coefficients, we're not really going to change. Okay. Now we could set the type of rising and falling edge, but we're just going to leave this as default for now. Now we can press OK. Now if we were to try and simulate this, what we would find is that this wouldn't work really how we wanted it to at all, because we haven't told it what our VDD is quite yet. So even though if we descend into this guide, even though we told it that VDD is connected up here and ground is connected down here, right now we don't have any voltage source connected to that VDD. So it doesn't know what VDD should be. It doesn't know if it's 3 volts, 2 volts, 5 volts, or whatever. So we actually need to give it a VDD as well. And the way we can do that is we can just pick the VDC source out of the analog line. I'll move it just right over here. Now, if I bring back up that instance window, I can pick that VDD symbol one more time, and I can just set it to the top, the positive terminal of this DC voltage source. I'll do the same thing. C to bring up copy this ground symbol, position, copy, bring it over. So now we are actually applying a voltage positive voltage to VDD relative to ground. So this is going to actually let us power these transistors. Now we need to set the DC voltage here, and the DC voltage we're going to set is just going to be the same as before, chip VDD. Now, hopefully if we save and check, we shouldn't get any errors, so that's good. So if we save and check, now we can actually launch ADEL, and we can bring up, excuse me, we can bring up the ADEL window. Now, hopefully you remember we do have to change something, so we have to click Setup, the simulator directory host, change it to Spectre. Okay. We also need to bring in the model libraries, so we'll go to Setup, Model Libraries. I'm going through this a little bit faster, but we spent more time on the previous video, so if you need a refresher, just go back to that video. We're going to load PTT and NTT since we have both transistors here. And then I'm going to copy from cell view all of our parameters. So let's just fill in some blank values. So let's make chip VDD maybe 3.3 volts. Let's make our period something like 10 nanoseconds and our rise time 100 picoseconds. So now currently we haven't told it what kind of simulation we need to do, so we can click this analysis button. Now DC is going to be the DC operating point, or we can sweep a variable or something like that and see the DC point. But for us, we want to see how this changes in time. So instead, we're going to use a transient simulation. Now, for the transient simulation, we only have to tell it a stop time. Now, we could, once again, hard code in like 20 nanoseconds to see 2 cycles of the pulse. But if we go back and change the period, then that doesn't really work well for us. What we can do is we can instead use variables here as well. So what I want to do is if I want to see, let's say, 2 cycles, I can say I want to see 2 times. And then if I do capital VAR to tell it we're going to be 2 times a variable that we've defined, open parentheses, open quotations, then I can just type in the variable names. I can use T, close quotations, close parentheses, and then I don't have to set anything else. So hopefully I can press OK. It's taken it so far. And then if I run this simulation, you can see it's generating a netlist. It's saying it's successful, but I'll believe it when I see it. So it seems like everything worked well. We can open up the CIW window just to verify that everything worked well. Close this here. CIW window says everything was successful. So now let's take a look at the output of. So we can actually do the same thing, results, direct plot, and then inform. Go ahead and click yes here. Now we're going to pick a voltage, so we're going to look at the output voltage. We're going to add it to the outputs. Now we need to make sure we're selecting a net on the schematic. So go back to our schematic, click this output net right here. We'll see that it got highlighted red. And now we should see on our output that, oh, this doesn't quite look right, does it? So to us, it may look like it doesn't quite look right, but we can give ourselves a nice reference if we also probe the input voltage. So let's probe the input voltage as well. Make sure I have this same direct plot form open. Go back here, our input, and it got highlighted pink. Now we can see that this is what our input looks like. This is what our output looks like. So it is getting something going on here, but it's not what we expected. And the reason is because our inverter is still pretty small, and that output that output capacitance is still pretty large compared to this inverter. So if we maybe drop this value down, I press escape to get out of that tool. If I drop this value down, instead of setting it and hard coding it, I'm just going to do C out. Press OK. Now, since we changed the schematic, I have to save and check. Now, if I come back to this window, I can copy from cell view. Let's make this like 100. Now, if I set it to be 100 and run it one more time, and now we should see the input and output. It's currently simulating. Hopefully we're still moving along. Alrighty, so I had my simulation lock up on me, so I had to get it back to where we were. But now we've gotten it so that we're pretty much back where we left off. So we're at 3.3 volts, 30 femtofarads for our C out. And we still have our period set to 10 nano and our rise time set to. So if we rerun the simulation, what we'll end up seeing is that now we have this purple curve. For me, it's purple. That is our input. That looks very ideal. And if we take a look at our output, this green curve, it is functioning as an inverter. You can see that there is that slight bit of delay. So it is taking a bit of time for it to rise and fall, and it is occurring slightly after this first one originally crosses that VDD over 2. Now, what we can also see is that it is actually falling quite a bit faster than it's rising, and that has something to do with the way that I designed it. So for your design, if it's going to be a better design, this rise time should be this rise time should be pretty similar to fall time. But what we can see is that if we're trying to do a more complex simulation, like if we wanted to have, for example, we go back to our schematic, if we wanted to have 2 inverters in series, so if I select these components, move them, and then I want to take this inverter, press C to copy it, and move it so that the input is now feeding the output, or excuse me, the output is now feeding the input of the next one. What we will see, if I make this really quickly, save and check, rerun our simulation, this may be slightly different just because we may not be probing the right output. Yeah, so you can see it does look different because we would expect our output to be pretty much in sync with our input, but we are actually probing probably this point still. We need to go back to our results, rect plot in main form, probing a voltage, adding it to the output. Now we're going to probe. See that it's dashed this time, but if we rerun it, maybe it'll change. Okay, so now you can see maybe if we get rid of this, let's see. Our net 1 is our input, net 2 seems to be the first output, net 3 is the second output. So let's go ahead and go back to this guy and let's just get rid of net 2. Maybe we don't care as much. We can right click it. We can just delete. Okay, now it's gone. Hopefully if we resimulate, we'll be back to it. Okay, great. So now you can see that for this output, this rise is taking a considerably longer time compared to this fall. So this fall seems to be happening a little bit faster compared to this rise. Now again, this is because of the design that I implemented. It wasn't the best design, but your job is going to be to fix it, make sure it's balanced and that it's working like a good inverter. What we can see is we can actually see this delay and we can use some markers to measure it. So we can use markers to measure it. We can also maybe split some of these strips if we needed to. Let's see. So we could also create a marker. We can create a horizontal marker. So if we want it to be right at, let's see if this is the right way of doing it. Divided by 2. Apply. Rerun if that'll. Not looking like it is. Let's maybe try adding a marker in, create a horizontal marker. We just do chip VDD over 2. Still not working. So either way, what we can do is we can actually select this horizontal marker, press Q to bring up the properties, and then we can actually move it to the known chip VDD over 2, so 1.65, and it will actually add these measurements so that we can see at what point it's crossing, and then how long it's taking for that to propagate to the output. We can use this to measure delay. Yeah, so those horizontal markers can be pretty useful. Now, what we were saying before is that if we have a multiple of these inverters, we want to have an easier way of going through and manipulating how each of these inverters works, right? So we want to have an easier way of manipulating maybe the multiplier on these inverters. So if I click one of these guys, I don't have that tool selected, click one of these guys, I'm going to press Shift X. So now we're going to do a descend edit. So now I'm editing this original schematic. One thing I could do is I could select both of these transistors, and I could make it so that each of their widths is 1.5 micrometer times M. If I select this other one, I can do the same thing, 1.5 micro times M. Save and check, and hopefully that's working well. Then we can go back to the top, save and check this one too. We go to our simulation window. What we'll see now is that if we do copy from cell view, we now have this new one M. So if I make this multiplier 4, now we're expecting it to be a more powerful inverter, and we're hoping to see a little bit better performance if we are successful during our. Okay, so we're back now after my simulation froze up once again. But what we can see is that if we rerun it now with the multiplier of 4, we're able to change the way that that multiplier works with this simulation window. But if we're trying to get an optimal delay, then we don't necessarily want both of these to be equal to 4. So we want a way of changing each one independently. Same thing if we have a fan out, we may want to change each individual gate in that fan out. So this way isn't really the best way of adding in a multiplier. What I'm going to do is I'm going to descend out of all my tools. I'm going to descend edit into this one once again. And then instead of doing 1.5u times m, what I'm going to do is I'm going to press Q, and we're going to do 1.5u times, and what we're going to use is we're going to use little p, big P, AR, open parentheses, open quotes. Let's use F. So then we can add all of this. And then what we'll see is that all of these equations down here have updated, but pretty much what this is telling us is that it's going to actually pass this parameter up to the symbol view. Now in the symbol view, we can independently say what we want each of these f's to be. So we can have one FB1 and another FB4 or something like that. So if we press OK, then we can do the same thing for this one down here. So I'm actually just going to be lazy and I'm going to copy and paste this right down here. Okay. And now if we save and check, we can see that everything's working well. Now, one thing that we have to do that I'm going to do pretty quickly is that we actually do have to update the symbol. So if we don't update the symbol, then what will happen is that pretty much the symbol is what's going to be speaking between the upper level schematic and the lower level schematic. So the symbol doesn't know about this parameter that we're passing up, f, so we're not going to be able to access it from the upper level schematic. Pretty much what we need to do is create a new cell view from cell view. We're going to do another symbol, press OK. It's going to say it already exists. Let's just modify it. Then we're going to press OK to give it these new parameters. And then hopefully here we can just, so it's going to tell us that what we changed and on what date and time. So it changed cell view properties for the port order. Hopefully we should be able to save this. I'm going to go ahead and close it. On this screen, we're going to go up to the top level. We press Q on this guy. So yeah, now what we can see is that we've updated the symbol to now have a new CDF parameter. So really quickly, just going to open up the symbol because this white text here is kind of cluttering up the schematic. I'm going to go to the library manager, open up the inverter symbol. Let's just delete here. Check. All of that closed out. Okay. So now we can see that our schematic looks pretty much the exact same that we had before. But now, if we click on one of these inverters, we can actually program between each one what we want that F to be. So now if we want to have our first one be a multiplier of 1, second one be a multiplier of 4, that's definitely something that we can do now. So now we can save and check. And then let's go back to our simulation window. What we'll see is that if we get rid of this parameter, now if we try and do copy, it'll let me. If I try and do copy from cell view, you can see that that M parameter has now just sort of gone away. So let's resimulate now. Hopefully we won't lock up. Okay. So now we're resimulating, and now we already have a results window open. Now we can see that that delay has actually improved somewhat. We've definitely improved our delay from the previous version. And if we wanted to go even just a step further, what we could do is we could maybe pick this guy, and we could say we want this to be a variable m, maybe. Save and check. Now if we copy from cell view here, we have that same variable m. And now I can maybe play around with this. Let's try making it 4, keep it the exact same way. And we can use tools, parametric analysis. And we can sweep m. Let's sweep from 1, 4 in 1, 2, 3, 4 steps. Okay. So now if we simulate, this is going to be the parametric analysis case, and hopefully lock up. So the first one was successful. Now we're moving on. This is taking a little bit more time because it's actually having to do the transient time domain simulation for each of these. But what we can see, hopefully, from the results, so for our input, it all looks the same. For our output, it all looks the same too, isn't that? Maybe we messed up some. Let's just try doing this manually. Let's forget about parametric analysis. Let's just make this multiplier 1 for now. Then we'll use the horizontal line that we had before to sort of measure the difference. So if we create a horizontal marker at 1.65, which is our VDD over 2, then we can see that our delay is approximately 700 picoseconds. So our delay on our rising edge is approximately 700 picoseconds. Let's do the same thing now with the multiplier of 4 and rerun. Exact same. What am I doing differently? Oh, so yeah, so the delay has been reduced some in this case. Well, actually, at the wrong point. So if I change this to be 1.65, yeah, so we can see that the delay is still about 700 now. Maybe if we set C out to be a bit smaller. Let's try about 10. I'm going to set M equal 1. Still looking the exact same. See what I'm doing wrong. So maybe one thing that we can't do is, do I have each of these set to M? Maybe we can't use a variable for this parameter here. So maybe we need to actually set this to 4. Now let's pull up this window. Rerun it. Oh, I forgot to save and check. Save and check. Let's set it back to the way that it was before. We'll keep it there. Hopefully now we will see. Okay, yeah, so it does look like it changed just slightly. So it looks like maybe we can't use these parameters whenever we're passing it into the symbols itself. So if you're going to do some modification like that, then you might need to use a slightly, excuse me, a slightly different. So you maybe need to manually update them all. Let's just try it one last time with do it with a more noticeable delay. So let's change the period down to maybe 4 nanoseconds with 10 femtofarads. Okay, then let's change this multiplier 1. Save and check. Rerun. Okay, so you can see that the performance is changing depending on that multiplier. So this is something that you can spend a little bit more time optimizing and going along with the homework problems just to check and see how these variables will affect it. But this gives you definitely a more convenient method of changing independently the multipliers and the size of each transistor. So this should give you the information that you need to go through and actually do the homework problems. If there is any questions that you have, please feel free to contact me either through email or in the comments below. And I hope you guys enjoyed, learned, and please let me know if there's anything that I forgot because I can update the video. All right, thank you guys. So just one last thing before we actually leave. So one thing I want to show you too, just to help make it a little bit easier to visualize maybe these multipliers, since we can't see it right now, and we can't change it from the simulation window since it has to be have that value to complete the net list. Then what we can do, excuse me, is that we can actually have it display these values on the screen for us. So if we click one of these inverters, we press Q, we can see that over here for display, we can either do the value, the name, or both. In this case, if we do both, what we'll see is that we may want to change our symbol slightly so that the instance number is slightly out of the way. What we'll see is that we can now see that f equals 1 here. And we can do the same thing for this guy with an f equal to 8. And then we can make sure that this one is set to both. And now we can sort of see how these values will affect it. That's just one last thing I wanted to show you guys. And like I said, if you do have any questions, please feel free to contact however is convenient for you. And I hope you guys enjoyed.